Okay, so this is another video lecture for Math 1133, Calculus for Business, Fall 2020. Um, we're still in Chapter 3. We're going to do Section 2. This will probably be shorter than the previous video, more like 30 minutes, probably. So, graphs of functions. We talked about what functions are and how to find features of them. So now we're going to talk about graphing them. So the graphs of functions are very important in calculus. So I want to start with just the general approach to graphing a function. If you're given some function and you need to graph it, and you don't have like a computer or calculator to do it for you, you've got to draw it by hand, right? Typically that's not going to happen, but you need to understand what goes into a graph. So if I just make up some graph, let's say f of x, or some function rather, f of x equals, let's just do something easy to start with, 2x minus 1. Start with the easiest thing we have. Now, some of you already know what that looks like. You're probably thinking, oh, I know the name of that function. I know what it looks like. I know the different features, and that's great because this is review, so you probably know at least some of that. But let's pretend that we don't. What would we do to graph this if we didn't already know what we're dealing with? So to start with, I'm going to make what's called a t-table because it kind of looks like a lowercase t when you get started. And I'm going to have an x column and a y column, y being the output variable. Or if I want, I can say the f of x column. It's basically the same thing. I'll talk about what I mean by that after we do this graph. We'll do a little interlude on notation. So what I can do is just start picking numbers like 0, 1, 2, 3, 4 for the x value, and then throw those numbers into the function and see what I get. If I plug in 0 for x, I'll get 2 times 0 minus 1, right? 2 times 0 minus 1. It's not drawing the best. So that's going to be negative 1, right? So negative 1 is the function value, or in other words, the output value or the y coordinate, okay? Let me change to a bolder color here so it's easier for people to see. If I plug in 1 into my function, right, then I'll have 2 times 1 minus 1. And at the end of the previous lecture video, we were talking about evaluating functions. So I'm basically doing repeated evaluation of the function at different, somewhat randomly chosen inputs in order to get some outputs, and then I can start graphing, right? So I'll get what 2 minus 1 is 1. Let me erase that. 2 minus 1 is 1. If I plug in 2 into my function, I'll get 2 times 2 minus 1, which will be 3. So 3 is the next output. If I put in 3, I'll get 2 times 3 is 6, minus 1 is 5. And if I plug in 4, 2 times 4 is 8, minus 1 is 7. Okay. So there are my randomly chosen inputs and then my outputs. And so if I want to start plotting or graphing, well, if I want to graph the function, I can start by plotting the points. So I'm going to need to draw out an x-axis and a y-axis. And I'll notice most of my values are positive, right? And you might recall that's going to mean that I need more of the positive x-axis and more of the positive y-axis. I won't need any negative x-axis because I didn't choose any negative x values, right? I started at 0, 1, then 2, then 3, then 4. I chose these numbers. So because of my choice in those numbers, I'm not going to need any negative x axis. So I'll make, I guess, like this. And I'm going to let the auto line tool, hopefully it will work with me. Sometimes it's a little fidgety. Here we go. So I'm going to I'm going to mark out some x and y units on the axes, but I need to look at what are my greatest values. My greatest y value, my greatest output is 7, my greatest input is 4. So I'm going to need at least 7 units vertically. And so really, maybe I should even lower that down a little bit. So let's go 1, 2, 3, 4, 5, 6, 7, right? And then negative 1, negative 2. 2 units below, which I don't really need, but so I've got 1 unit extra below the axis. That's fine. And when I go do my horizontal markings, they don't have well, let's put it this way. When I drew these out, I tried to make them roughly equally spaced just because I want a reasonably accurate graph. And those are pretty good, you know. They're not as good as a ruler, but they're pretty close. So when I go to the other axis, these need to be, you know, equally spaced. Wherever I put them, they need to be equal. And if I want, I can make them larger. They do not absolutely have to be the same spacings as these, although I might choose to do that. But however I choose to space them out, they should be roughly equal. So I'll try to keep them the same as the vertical. So 1, 2, 3, 4. So let's go to 5. So not perfect, but you know, good enough for doing it by hand. So now I can go plot these pairs of points. This input-output pair of 0, -1, that's going to make a point right here, right? And this input-output pair 1, 1, make a point like right here, 2, 3. Horizontally 2 units, vertically 3 units will be like right there. And then 3, 5 is like right here. And then 4, 7 is like right here, right? So I'm getting a straight line out of that. So something like this, right? And I'm trying to make it as accurate as possible. And in fact, this it's -2. I'm going to move to the other side. This isn't super important. I'm being a little over careful at this point, but that's fine. So this was off by a little bit, but that's fine. So that's why I kind of did the points roughly first, and then I did a little bit more carefully. So now I can go fill in these points, and it looks like I was more careful from the beginning. If I draw the line and then put the points afterward, if that makes sense. If you know how old school cartoonists would work, where they draw out in pencil and then they would ink and then erase the pencil, I'm kind of doing that. So it looks like the finished product looks really nice because I you know, was erasing the things that were off by a little bit. Anyway, that's not super important right now. I'll go off on a tangent from time to time. Sorry about that. So anyway, we get this graph. I'm connecting with a line because I'm putting the points down, and they sure look like, yeah, this makes a line. And so for some of you at the very beginning, when I wrote this out, you think, oh yeah, it's a linear function, right? 2x minus 1, that's got a slope and it's got a y-intercept, right? And you can look at the rise over run of this is, you know, 2, right? We'll talk more about those specifics of linear functions in section 3, I believe. Let me double check that. It is section 3. Yeah, section 3 is more on linear functions, so we'll see more about that in section 3. So I just wanted to do as simple an example as possible for our first example in this section of how do you graph when you don't already know what you have. So now I want to do just a few more examples of this. We'll do a few examples of graphing functions we don't already know how to handle necessarily just by this approach. And then we'll move on to the next topic. So let me do something a little bit more complicated, and some of you will think this is not that hard. How about something like this? 4 minus x squared. And some of you are thinking, oh yeah, I know what that is. That's easy. But let's pretend that we don't, right? So I'm going to make my table. Okay, and my x column and my, oh yeah, I almost forgot to talk about f of x versus y. So let's do that. Let's do that over here. So I'm going to switch colors as well. So when I say f of x, well, let's back up even further. If I say y equals 4 minus x squared, right? This is an equation in two variables. We have typically x is our input variable, typically y is our output variable. And so if you look at, does this produce a function? Does each input produce only one output, right? Then yeah, it does. It turns out this is a function. Y, this equation gives y as a function of x. It gives y as a function, abbreviating here, function of x. Okay? So we'll say that x is the independent variable and y is the dependent variable. Y depends upon what x is. So what I can do is say, well, I don't really need to refer to the output variable. I want to emphasize the function name, f of x. And one of the reasons I might want to do that is that later on, I might want to represent function evaluation. Like if I wanted to do the difference quotient, if I never call this f, how do I represent the difference quotient? How do I refer to f of x plus h, right? I would, if I want the difference quotient, delta y over delta x, which this might not be familiar yet. We'll talk more about this later. It's something I referred to in the previous lecture, but we'll get more detail on it later. This is f of x plus h minus f of x all over h. So how would I refer to this, the difference quotient, if I'd never talked about f as a function with an input in the parentheses container? So this is just a way of referring to the formula 4 minus x squared without having to write 4 minus x squared every time. Because I could totally, instead of writing this, I could write, because this is equivalent, and in fact, let me move this over, because I don't want to take up a whole lot of vertical space. This is the same as 4 minus x plus h squared minus 4 minus x squared all over h, right? It's the same thing. I'm now utilizing the formula. So the benefit of having f of x as a way to reference the function is that you can refer to the difference quotient without writing the formula out every time. So especially if your function is really complicated, I want to say, okay, what's f of x plus h? I want to refer to it. I want to say, okay, we're going to talk about f of x plus h. I don't necessarily want to have to say, okay, we're going to talk about 4 minus x plus h in parentheses squared. I'd rather just say f of x plus h. It's just a convenience. It's a way to refer to it. So these two things, y and f of x, are basically interchangeable. They both refer to the function, but one of them emphasizes the output variable, one of them emphasizes the function name and the input variable. But they're functionally, that's a bit of a bad pun, they're effectively equivalent. They mean the same thing. So when I say delta y, this means the change in the function outcome, the change in the y variable. This will make more sense when we get to chapter 11 and we get more detail on delta y and delta x. What are those things? For now, this might be a little unclear. So I'll probably refer to this again later as well when we get to that detail. Anyway, if that connection here doesn't make a lot of sense yet, that's okay. We're going to build that connection. You might not have heard it phrased that way before, I guess. Anyway, we'll build upon that connection if it's not clear already. So that was just a bit of an aside. Okay, so back to graphing this thing. And in fact, what I think we'll do is move this down here so that that's more out of the way. Yeah, let's do that. Okay. So I need to pick some random values. So I could go 0, 1, 2, 3, 4, and that would work fine. But for this one, I want to include some negative inputs as well. So let's go like negative, say, negative 2, negative 1, 0, 1, 2. All right? Somewhat random. Not entirely. And part of this is that I know what the graph is going to look like. I could have gone 0, 1, 2, 3, 4, and that would have been fine, but we didn't use any of the negative x coordinate. I'm sorry, negative x axis in the previous one. I want to use some of the negative x axis in this one. So if I take negative 2 and I plug it into my function, I'll have 4 minus parentheses negative 2 squared. And this is easy enough that you probably don't need a calculator for this, right? This is small numbers, not too hard. If you, especially when the numbers get larger, when you are using a calculator, make sure that you always use parentheses as needed. So if I were to type in the calculator, again, these numbers are small enough, you don't need a calculator, but if the numbers were bigger, you might. If I type this in the calculator, the minus button in the calculator and then the negative button in the calculator, right? Those are not the same thing. When you're writing by hand, these look the same, but in a calculator, they're different. This is not correct. This will give you 8 in a calculator, right? We really do want the -2 to be in parentheses in the calculator as well. Otherwise, we're not going to get the right result. So both in handwriting, these are not really distinguishable easily. You need parentheses anyway. But in the calculator, if you don't use parentheses, you'll get the wrong result, right? This is not correct. We should be getting 0 there. Okay, so, need to change the option on the eraser there. Okay. Sorry if I'm a little distracted. I'm getting a bunch of notifications on my iPad screen while I'm doing this, which you don't see, I hope, but yeah, I don't think you do, but it's a little distracting. So I get 0, right? Now if I plug in -1 into here, I'll have 4 minus, in parentheses, -1 squared. -1 squared is 1, right? -1 times -1, you get 1. So 4 minus 1 is 3. So I get 3. If we plug in 0, okay, 4 minus 0 squared, well, 0 squared is 0. 4 minus 0 is 4. Okay, now if I plug in 1, okay, 1 squared is 1, so 4 minus 1 is 3. And plug in 2, 2 squared is 4, 4 minus 4 is 0. Okay, so you might notice something here, maybe not, and I won't point it out yet. I'll just go ahead and start drawing. Now I notice that I don't have any negative output values, so I don't need necessarily any negative y-axis space. But I do need both positive and negative x-axis space because of how I chose my sort of random numbers. I was doing air quotes there. Of course, you can't see it. I was doing sort of random numbers. Not entirely, because I wanted to use x-axis, both sides of the x-axis on this one. So something like this. My biggest number is a 4. None of my other numbers are very big, so I'll go 4 units vertically. 1, 2, 3, 4. Let's go up to 5. And then horizontally, and I'll mark -1, -2. And horizontally, I'll try to keep roughly the same spacing. So 1, 2, 3, let's say 4. So -4 there, and then 1, 2, 3. Too far. 4 there. And I'm trying to keep it spaced, not perfect, of course, but I'm trying to keep it pretty close. So now I can go plot this ordered pair, -2 for the x-coordinate, 0 for the y-coordinate. So like right here, right? Which I'll erase the highlighting later after I get this a little bit marked down. -1, 3, so like right here, roughly. 0, 4, so like right here. 1, 3, so like right here, and then 2, 0, so like right here. It's kind of like a triangle a little bit, right? Maybe it's a triangle. Well, if we're not sure what this is supposed to look like, and some of you are probably thinking, yeah, no, you're probably shouting at your screen. It's called this. I know what it is. But let's pretend that we don't know. So how would we, this is not so clear what this is. How would we get a clearer picture? In an in-person class, I would say, okay, guys, what should we try? And pretty quickly, someone would say, and maybe you want to pause this and think about it for a few seconds, but pretty quickly someone would say, well, shouldn't we just pick another x value and see where it goes, see what it looks like? And I would say, that's great. That's a great suggestion. What x value should we pick? And someone might go 3, because 3 would be like the next. If you think about this as being a progression of numbers, 3 would be the next one. And I would say, yeah, we could try 3, but let's do something else. Or I would say, let's do 3. In fact, let's do that. So let's do 3. If I plug 3 into my function, what do I get? Right? So 3 squared is 9, so 4 minus 9 is -5. Oh, okay, so we're going to need a bunch more negative space. So, and that's okay. If you realize, that lined up really nicely. I'm going to need a lot, because I have to go down to negative. Well, no, -5. That's not too bad. Okay, so here's -2, -3, -3, -4, -5. I'm trying not to shout into the microphone when I'm closer to it. Okay, so 3, -5. That's going to be like right. And you know what? I'm going to go ahead and make those solid points. And then I'll try to erase the highlighting without erasing the solid points. Oh, and I didn't mark the -5. I'll do that in a second. In the t-table, in the list of numbers, -5. Okay, well, this still kind of looks like a triangle, so that didn't help that much. So someone might suggest, well, why don't we try something something that's in the same general region? How about like 1.5? Okay, if I put in 1.5, 1.5 into my function, 1.5 squared, you might know, is 2.25. So if I subtract it, I get 1.75. 4 minus 2.25 is 1.75. Okay, so here, 1.5 is like right here, and 1.75 is like right there. It's like right there. Hold on 1 second. I had to sneeze, so I paused the recording. Okay, so like right there. And in fact, I'm going to erase this. I'm going to try to put that point down right there. And we get a better picture of what's going on, right? And if we do more of them, we'll start to see, if we do, do more points, we'll start to see that we get something like this. And I'm going to stop that part there, and then on the other side, you'll end up with something very similar, like this. Okay? And you might recall that this is called a parabola. This is a graph of a quadratic function, right? You might recall that from your algebra class. So we're actually going to talk more about more detail on quadratic functions in section 4 of chapter 3. So I just wanted to do one example, sort of with guesswork, picking x values and just trying them out and seeing what we get. And this here, if you didn't already know what you're looking at, this here might not be enough to get this graph, but you just do more points. If you think about it, when you have a computer graph something for you, right? It shows up on a screen. Well, what is it doing? Well, depending on how the computer, that software is programmed, well, it's picking a bunch of x coordinates, throwing them into the formula, and getting a bunch of y coordinates, and then it's making an image file, right? It's a what's the word I want? A bitmap, right? Each x coordinate and y coordinate will be a pixel, right? Each pixel is assigned an x and y coordinate, and then each pixel is assigned a color value, black or white or gray or whatever, depending on the resolution, I guess. And then the screen shows where the graph is present. That pixel gets black or blue or whatever color you pick. Where the graph isn't present, it's white, right? So then you see the graph like on the screen, like what you're looking at right now. This graph right here, right? The computer is drawing that on the screen, and if you look really closely at your screen, especially if you have an older computer or something, if you have like a really new smartphone, you can't see the pixels. But if you have like an older monitor, especially, you can see the individual pixels, and some of them are colored, black or gray, and others are colored white or just really pale gray. So what we're doing here is kind of like what a computer would do. You pick some x values, you figure out the y coordinates, and you graph them or you plot them, and then you get a graph emerges out of those individual points. Anyways, that's our general approach to graphing. I want to do a few more examples using other kinds of functions, and then we'll talk about how to tell. After that, we'll look at how do you tell if a graph that you're already looking at, not building a graph, but looking at a graph, does it come from a function or not? So the next example I want to look at is what's called a piecewise function. In fact, let's do this. Sometimes it's called piecewise defined, so I guess I'll call it that. What that means is the function is defined in pieces. So maybe that was predictable. What does that look like? So I'll make a simple example. Let's say that your function, the output is x plus 1 whenever x is greater than or equal to 1, and your function is 1/2 x whenever x is less than 1. So there's two different formulas, and you might go, well, hold on, you told us that to have a function, each input can only have one output. Well, That's fine in this case because this formula only gets used for inputs that are at least as big as 1s, like 1, 2, 3, 3.5, numbers like that. Then there's the auto rectangle tool trying to help me out there. Whenever the input is larger than 1, well, equal to or larger than 1, then you use the top formula. If you put in an input that is less than 1, you use the bottom formula. Okay, so there are two formulas, but they're not used at the same time. Which formula you use is determined by what kind of input is coming in. How big is that number? Or how large is that number, I should say. So I don't know what this looks like. Let me start making up some values. Let me make a t-table. In the next section, when we get more detail on linear functions, we won't have to make a table to graph this kind of thing. So let's say here's my x coordinates, here's my y coordinates. Now, I definitely want to include, I would definitely want to include 1, because that's where the distinction between which formula you use goes. In fact, I'm going to do 1 twice, and I'll tell you what I mean in a second. So I'm going to list 1 twice, and then above the first one, I'm going to list some other numbers that are less than 1, and then below I'll list the numbers greater than 1. So I'll do 0 and -1, and I'll do 2 and 3. So I'm doing 2 values this time. Why am I doing why am I doing the number 1 twice? Well, I'm going to do it here, of course, because if you plug in 1 to the function, then that's the formula that gets used. But also, I want to do, and I'm sort of cutting to the chase here. I'm getting ahead of myself a little bit, but you'll see what I mean. Because this formula gets used like for 0.9 and 0.99 and 0.999, I want to say, well, where would that piece of the graph start? This one starts and stops at 1. This one starts and stops at 1. So I want to mark that location. You'll see what I mean. We hope anyway. So I guess I just need to start plugging these values in. So if I plug in -1, well, that's less than 1. So plug in -1. 1/2 times -1 is -1/2. So -1/2. 0. If I plug in 0, well, that's less than 1. So if I plug in 0 there, I get 0. 1/2 of 0 is 0. If I plug in 1, well, now I'm using this one, right? But what I'm going to do is this. I'm going to say, let's still use this one for the bottom one, because that's what we've been doing so far. So I listed it twice, because I want to see if I were to use the bottom formula still, where would that be located? Okay, and you'll see why I do it in a minute. So if I plug in 1, 1/2 times 1 is 1/2. Okay, so I'm going to use the bottom formula for all 3 of these, even though this one really, we should be using the top formula, but you'll see what I mean. So now for the rest, I'll use the top formula, because now these are all at least 1. So if I plug in 1, use the top formula, 1 plus 1 is 2. If I plug in 2, 2 is greater than 1, use the top formula, 2 plus 1 is 3. And then if I plug in 3, 3 is greater than 1, use this formula, 3 plus 1 is 4. Okay, so I'm going to start by looking at my numbers. How big are they? Well, my biggest number is 4. Most of my y coordinates are positive. I just have the one that's negative. So I don't need a whole lot of quadrant 3, right? So let's do this and this. I'll go ahead and mark out vertically first. So 1, 2, 3, 4, 5. I made these a little closer together than the previous example, but that's okay. 1, 2, 3, 4, 5. And then we'll do like 1, 2. Okay. So when I go and I plot out, let's start at the bottom. I'm going to plot out this guy. I'll do 3, 4 first. So 3, 4. That's right about there. Okay. 2, 3. So 2, 3. It's right about there. 1, 2. It's right about there. Okay. Now, because this formula in the inequality that tells you when to use this one, we have x is greater than or equal to. These are all solid filled in points. Okay, so I'm gonna go ahead and fill those in and try to make them as neat as possible, because I do want it to look relatively accurate, okay? And I'll get rid of the blue highlight later if I need to. Now what I'm going to do is I'm going to switch to starting at the top here, okay? So -1, -1/2. So right about here, okay? And then 0, 0, so right here at the origin, right? And then 1, 1/2. So right about here, okay? So now if I connect, well, let's not connect yet. Let's go ahead and start filling these in. So fill that in, fill that in. But remember, this formula we should not actually use. So when I go to fill in this last, sorry, wrong marker. When I fill in this last position, I don't make a solid dot, okay? Because we're not using that formula. This is merely the location where we stop using that formula. Because if I plug in like, say, 0.5 or 0.75 or 0.9, those inputs all use that bottom formula. So they're going to continue this linear pattern up to that point, and then they're going to stop. And I'll leave an open circle there because I'm not using the bottom formula at 1. The graph jumps up to the next formula. Okay, so from here I'll have a solid filled in dot, and I'll continue that pattern. And of course, I'm only taking a couple of points to mean that there's a line, but I know that these are linear formulas that I'm using. Okay, so my graph looks like that, and I can get rid of some of this extra stuff. Try not to lose anything I need here. Okay, and I think, yeah, cool. And I still got some blue highlight here. I'm not going to worry about it. So there we go. That's what the graph looks like. So what I'm going to do in the future when I plan this out, instead of, I was being a little cryptic here. It wasn't clear what was happening, but hopefully now that you see what the result, this one produces the solid circle because we're using this formula where we are using x plus 1 when x is equal to 1. And then here, this produces this open circle because we're not going to actually use this formula at 1. It's just at 0.8, 0.9, 0.99, we are using that formula. When we're really close to 1, we still, if your input's less than 1, you're still using that formula, that linear function with slope 1/2, right? But then there's a gap in the graph. They don't connect, which is going to happen sometimes when you have this piecewise defined function. Okay, so that was just our first example of a piecewise defined function. Hopefully that all kind of made sense. And if not, during the class meeting, we can do another example. We can expand upon this and make the idea clearer. So I want to switch over to, let's do one more example, and then we'll switch over to the other concept. So the next kind of function that we need to talk about is what's called an absolute value function. Right? F of x equals the absolute value of x. And some of you probably already know what this looks like, but we'll pretend that we don't, and we'll make a table. And I was expecting this video to be 30 minutes, but we're a little past 30 now, so it's probably going to be more like 45, actually. So x, y, and just pick some values, so like -2, -1, 0, 1, 2. And if you're familiar with absolute value does, absolute value says whatever your input is, throw away any minus sign that is present in the value. So if you plug in -2, you just throw the minus sign away. So the absolute value of -2 is 2. Another interpretation of what absolute value means is what's the size of the number? How big is it? We don't care plus or minus, just how big. Another interpretation is on the number line, how far is it from the origin? How far is it from 0? So on number line, if I say here's 0, here's -2, absolute value is what is that distance to 0, which would be 2 units, right? If you're over here at +2, what's that distance? Well, that's also 2. It's on the other side, but the distance is 2. Okay, so get rid of this. Okay, so absolute value of -2 is 2. absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Okay, so none of the outputs are going to be negative. They're all either 0 or positive. So when I go to make my graph, I'm not going to need any negative y-axis. Okay, so I'll mark out, so 1, 2, 3. I don't need a whole lot of, none of my numbers are very big. I don't need a whole lot of markings. 1, 2, 3. 1, 2, 3. So when I go to mark this point out, -2, 2, well, that's like right here. -1, 1 is like right here. 0, 0 is like right here. 1, 1 is here. And 2, 2 is right about here. So if I go fill those in a little bit more precisely, so roughly like that. Okay. Now, if I do more points, like if I just say, oh, what if I plug in 3? What do I get? Well, absolute value of 3 is 3. So that would then be like this. So you might notice, it just seems like this is a straight line. And it is. And if you plug in -3, well, if you plug in -3, absolute value of -3, that's 3. And it kind of seems like, and this is off by a little bit, but I guess I'll just correct that afterward. It seems like, this is just a straight line. See, it's off by a bit. So it really should be like right here. It is by hand, it's not going to be perfect. So you get this V shape, but this does connect. Why is that? Well, up here in this formula, when you plug in 1 to the top formula, you get 2. When you plug in 1 to the bottom formula, you get 0. They're not this, or sorry, you get 1/2 rather. Sorry, I was thinking about 0. If you plug in 1 to the top formula, you get 2. You plug in 1 to the bottom formula, you get 1/2. They're not the same thing. So there's no connection. There's a disconnect in the graph. In chapter 11, we'll have a term for that. Here, we just have one formula. There's not 2 formulas, right? Well, actually, depending on how you look at it, where do I have room? Let's put it over here. If you look at the absolute value of x and think about, okay, well, what does it do? It says if your input is positive, just keep it. If your input is negative, throw away the negative. So this is also a piecewise function. This says your input is just x. You don't change anything if the number is at least 0, if it's not negative. Now, your output is negative x if the input is negative. So if you plug in -2, the output is positive 2. You negate that to get rid of the negative that's there. So if you plug 0 into this formula, you get 0, right? If you plug 0 into this formula, you also get 0. -0 is just 0. So the two formulas don't have different outputs. When you plug in 0, they're the same, which is why we can just have the one formula. Okay, we don't need to refer to it in two separate formulas. We just say, well, you throw away the minus if there is one. That if, well, that's what these guys say. If the input's negative, then you do this. Well, that's a distinction on what the input is. That's a piecewise function. It just happens that this one, there's no disconnect. The two pieces agree at x equals 0. Okay. And so, in fact, if you wanted to, you could go over to this one. If it doesn't want me to zoom in, typically you don't do this with a piecewise function, but you could say that, and there wouldn't be a problem because the two formulas agree at 0 anyway. You don't need to do that. And if you wanted, you could switch the or equal to down to the other side, either formula or both. Not neither, because then what happens when x is 0? It has to be one of them. So yeah, so that's an example of a piecewise function that you've probably seen before. So last thing is I want to talk about how do you tell when a graph makes a function or not? So when does a graph make a function? So far, all of these have been functions because we're starting with a function. If I have something like this, like a parabola, well, let's do a little bit better, like that, right? Parabola. And I compare it to something like this, like a circle. We'll use the auto circle tool. These are very different with respect to which one is a function, which one is not. If I go and mark out this input value, this x-coordinate, so x equals whatever, I don't have numbers attached, and I look at the graph, and I look up, and I look at where are the y-coordinates that correspond to this x-coordinate, right? Y1 and Y2. There are two outputs, two y-coordinates that go with that x-coordinate, that input. This is not a function. Whereas with this one, if I pick some x-coordinate and I look up on the graph at the y-coordinates, where does the graph have a point with that x-coordinate? Then no, well then there's just the one value, just the one y-coordinate that goes with that x-coordinate. This is called the vertical line test. Okay, so the vertical line test is basically this. You look at the graph and you attempt to mark down a vertical line that hits the graph more than once. And if you can do that, well, then that graph is not a function. It fails the vertical line test. But if you can't, no matter where you put that vertical line, like if I were to grab this guy and slide it around, if it only ever hits the graph at one place, well, then it passes the vertical line test. Whereas with this one, as long as it's, I guess if I put it like right here, it hits just the one time on the edge of the circle. So at that location, there's only one output for that particular input, right? And then also over on this other side, if that input, that x coordinate, whatever that is, only has the one output coordinate, the one y coordinate, but everywhere else in between, no matter what x coordinate I pick, all of these have two outputs. Let me see if I can put that back. Yeah, close enough. So lots of graphs don't correspond to functions. Lots of graphs do. So if I pick an equation, like if I say, okay, y squared equals x squared, right? If I make up an equation, I can ask, okay, well, does this make a function? And you can pick x values, try to solve the equation. Do you get more than one y coordinate, right? So what does this one look like if you graph it? Well, this one's a little weird. I'm going from memory here. I'm not gonna plot out points, but you could if you wanted to. Here's my x-axis, here's my y-axis. What does the graph look like? And I'll do it in blue so it stands out a little bit. Well, I'm gonna have to build it over here so I can get the auto snapping to work. Yeah, I wanted to snap to 45 degrees. So that is what this one looks like. Okay, so does this pass the vertical line test? Does this equation correspond to a function? Well, it's pretty easy to check. Just make a vertical line. Oh, it hits the graph twice, so this fails the vertical line test. It doesn't pass because I was able to hit the graph twice with a vertical line. So up here, this one fails the vertical line test. This one passes the vertical line test. No matter where I put that vertical line, it's only going to hit once. Okay. So when you have an equation or a formula, you can pick numbers and try to find a way to get a double output, two outputs for one input, and that goes, oh, that shows you, oh, there's no, that's not a function. How about this one? How about y squared equals x? So if you graph that, it looks like this. And you might be able to tell right away, well, if x is 4. Are there 2 y coordinates? Right? If you solve y squared equals 4, do you get 2 results? And of course, yeah, you get 2 and -2. So if you graph this one, it looks a little bit like this. It's like a sideways parabola. So if you make a vertical line, this hits twice. So this fails. Okay. So when we want to do calculus when we want to do calculus on things that are not functions is more complicated and can be problematic. We want to stick to functions whenever we can. Now you can do calculus on equations that are not functions. These are called relations. So an equation that does not represent a function is called a relation. An equation that does not represent a function, does not. A function represents a relation. The equation relates the two variables. So both of these are relations. The x-coordinates and the y-coordinates are connected by an equation, and if you pick an x-coordinate, you can find out what y-coordinates go with it, or in some cases, there's just the one, right? Like at the, I'm getting ahead of myself a little bit, but here at the vertex, there's only one y-coordinate at that point, right? So there might be some places where the graph passes the vertical line test, but it would have to pass everywhere. If it fails at even one place, it fails the test. So in chapter 11, we'll be talking about derivatives of functions, and we have to start with functions. And then in chapter 12, we'll do basically 12 is on applications of functions, or I'm sorry, applications of derivatives. And so we'll start out continuing with derivatives of functions, but in chapter 12, we will have 2 sections on derivatives of relations. That's just a little bit more complicated, so it comes a little bit later in the course. Anyway, so this video is longer than I thought it would be, so I guess we will end it there. The next video will be 3.3, and it will talk about some more detail on linear functions.